Recording, all right. Okay, so going on to the schedule, let's see. So today is Thursday, September 17th, all right. The homework for Chapter 1, which covers all this stuff, 1.1 through 1.10, not 1.11, although that wasn't too bad anyway. That's due tomorrow at midnight, Friday, September 18th. But today we're continuing on with Chapter 2. Chapter 2 and Chapter 3 are both going to be due much later, Friday, October 9th. Okay, and in the meantime, I can finally get some grading done sometime in here. It's been a long time. All right, and we'll have some time for questions today, but we will continue on with Chapter 2. All right, any general questions before we start? Any general questions before we start? All right. So let's get started.
Hi, everyone. So where are we? First off, as far as the notes go, starting in Chapter 2, we're going to go back to my older online notes.
Okay, that's a little too early. Let's go to, that was Tuesday, this is Thursday. All right.
Hi, everyone. In section 2.3, we're going to divide polynomials, and we are setting ourselves up for studying rational functions in section 2.6. So we're going to start with long division, and then we'll talk about synthetic division in the second half. Now, long polynomial division has a similar flavor as old school long division with integers. So let's do a review. Divide 9 by 4 using long division. I am not kidding. It's a lot like factoring. If you don't know how to do the more advanced examples of factoring, go back old school and look at the more basic examples. Let's look at a basic case of long division with integers. 9, which is called the dividend, goes in here. 4, which is called the divisor, goes out here. Again, some terminology. Nine here is the dividend. 4 here is the divisor. We're dividing 9 by 4. Okay, then we ask what? We ask, how many times does 4 go into 9? Or, more precisely, when you divide 9 by 4, what's the quotient? Well, 4 goes to 9 twice, 2 times. Choose the quotient. And then what do? We multiply. 4 times 2, the divisor times the quotient. 4 times 2 is 8. So we multiply. First we find the quotient, which was 2 here, and then we multiply. And then what do we do with this product? 8. We subtract it from the 9. 9 minus 8 is 1. And what do we call 1? 1 is called the remainder. And we know we're done because the remainder is either 0 or it's a positive integer less than the divisor. 1 is less than 4. If we'd gotten 4, 5, or 6, we would have made a mistake. So we're done with this process here. Now it's a matter of writing the result. Remember, 2 is the quotient, and we're adding something. We're going to add a fraction. We're adding what? The remainder, 1, over the divisor, 4. So in other words, what we have so far, when we divide 9 by 4 using long division, when we divide the dividend 9 by the divisor 4, we get the quotient, 2, plus the remainder, 1, over the divisor, 4. And we normally write this as a mixed number, 2 1/4. 9 divided by 4 gives us 2 1/4, or 2 1/4. Now bear in mind that when we do polynomial division, we're going to need to keep this plus sign. For polynomial division, keep the plus sign. You're not allowed to put these two things right next to each other in polynomial division. So we're going to need this plus sign in polynomial division. But polynomial division is a very natural extension of what we just did up here. So to recap, when we divided 9 by 4, our ancient example of integers, when we divide 9 by 4, we got the quotient, 2, then we have the plus sign, the remainder, 1, which was less than the divisor, 4. And this was 2 1/4 as a mixed number. By the way, if you multiply both sides by 4, you get this over here. Nine equals 4 times 2 plus 1. It's kind of like an imperfect factoring. 8 is 4 times 2 with a 0 remainder. 9 is 4 times 2 plus 1. 1 is the remainder. This is referred to as the division algorithm. It may not seem like much of an algorithm, but it is called the division algorithm. And we'll see this as well. So when we go on to polynomial division, once again, we're going to divide a dividend by a divisor. We're going to get a quotient plus a remainder over the divisor. And we're hoping that the remainder will either be 0 or something nice that will make this whole thing a proper rational expression. We need this here, this fraction, to either 0 or a proper rational expression, meaning that it's what I call bottom heavy. The degree of the remainder has to be less than the degree of the divisor. So we need the remainder to either be 0 or we need it to be a proper rational expression that's bottom heavy, where the degree on the top is less than the degree on the bottom. That's kind of like in the old school long division, where 1 had to be less than 4. The remainder had to be less than the divisor. And then we get the division algorithm result over here by multiplying both sides by the divisor. Okay, we're going to do an example next time.
All right. Any questions before we go on? We are going to do an example. Any questions so far? All right.
Hi, everyone. We are now going to use these ideas in order to work out this problem. We're going to use polynomial long division to divide the top polynomial, the dividend, by the bottom polynomial, the divisor. In 2.6, we're going to look at this as rewriting a rational expression. Now, there are a couple of things that we don't like about the polynomial on the top and on the bottom. For one thing, the polynomial on the top and the polynomial on the bottom are not written in what form? These are not written in descending powers form. And usually that form is very helpful. So I would recommend writing these in descending powers form. But there's another issue. These two polynomials are both missing a term. What term are they missing? They're both missing an x term. So it may help us accounting-wise to actually write out a plus 0x. We call that a missing term. Writing out a missing term, we're calling that putting in a missing term. So these are two things that will help us out. Writing the two polynomials in descending powers form, and also writing in the missing terms. So let's do that. Now, technically it's an optional step, but it's really, really helpful to write the descending powers form. So on the top we have 6x cubed plus 3x squared, and eventually the minus 5. On the bottom we have the 3x squared first, and then the plus 1 at the end. Many students also benefit from writing the missing terms, especially the plus 0x in the numerator, or the dividend. The plus 0x in the bottom, students may not need that as much, but some students may benefit from that as well. As you do the homework, try to figure out if you really need the plus 0x in the divisor. Many students benefit from the plus 0x in the numerator, because if you don't do that, you tend to misalign your columns. All right, so descending powers of x, and I would suggest putting in the missing term placeholders. All right, so let's begin the long division. So again, we put the dividend, the numerator, the top thing, inside that symbol. We put the divisor, the denominator, the thing you're dividing by, the divisor here, that goes on the outside. Again, many students benefit from putting in this missing term, the plus 0x, in the dividend. Some students may also benefit from putting that in the divisor. But for other students, it might just be a bother. So do the homework and see what works for you. But remember, you want an accurate answer. So be accurate. More than anything else, be accurate. Okay, so remember, in old school long division, when we divided 9 by 4, we found the quotient. We asked, how many times did 4 go into 9? That is, when you divide 9 by 4, what happens? What's the quotient? Well, here, we're going to be looking at the leading terms. The leading term of the divisor is 3x squared. The leading term of the dividend inside is the 6x cubed. Informally, we're asking, how many times does 3x squared go to 6x cubed? Right. Although that's a bit awkward to say. More precisely, we want to work out this quotient. What is 6x cubed divided by 3x squared? What's the result? The result is 2x. And that's going to be the leading term of our quotient. It may not end up being the entire quotient, but it will be at least the leading term of our quotient. Now, we're going to try to line up like terms. So I'm going to put the 2x in the x term column. And that's one of the reasons why it's helpful to put in the missing term, the plus 0x, because it reminds you that something's there. At the very least, if you don't put in the plus 0x, at least leave a blank space in there. Don't put the minus 5 here. Leave a blank space in there so that you have an x term column. But again, it's a good idea to put the plus 0x here, and then you put the 2x in the quotient up on top. All right, so once again, the leading term of the top, 6x cubed, divided by the leading term of the bottom, the divisor, 3x squared, we get 2x, which goes into the quotient. It may not be the entire quotient, but it's the leading term of the quotient. All right, so once we got the 2 here, what do? We multiplied. We found that 2 was the quotient here, then we multiplied the divisor and the 2. 4 times 2 is 8, so we multiply. So here, what do? We take the 2x, we take the 2x here, and we multiply it by the entire divisor. So let's do it. What do you get? 2x times 3x squared is 6x cubed. 2x times 0x is 0. Again, for some students, this is a bother. Other students can use it well. 2x times 1 is 2x. All right, so once again, multiply 2x by the divisor, and we're going to write the product on the next line. Again, I encourage you to line up like terms to avoid confusion. The missing term here can be helpful. All right, so we multiply. Again, 2x times 3x squared is 6x cubed. 2x times 0x is 0. I'll write it as 0x squared. So for students who like to go thump, 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 it might be good to have the 0x out here. 2x times 0x is plus 0x squared. So you have something in the x squared term column. And then 2x times a positive 1 is a positive 2x. That goes in the x term column. Again, it's a good idea to put the plus 2x over here instead of over here or over here. So that's where these indicated 0 terms, these written missing terms, can come in handy. Whether or not the 0x here helped you or not, that depends from student to student. Many students benefit from this, and sometimes students benefit from this. All right. Now, we have the product. What do we do then? 2 times 4 was 8. And what do? We subtracted. We subtracted the 8 from the 9, the dividend. All right. But here's the thing, folks. You are much better than adding than subtracting. I'm telling you that right now. You are much better at adding than subtracting. So when you subtract something, what are you doing? Right? 9 minus 4. How do you rewrite this as an addition problem? Well, it's 9 plus what? It's 9 plus negative 4. So to subtract something, you add its opposite. So here's what we're going to do. I'm going to take the opposite of this middle line here, and then we're going to add. We're going to combine like terms. Remember, we must subtract the product from the dividend. People have an easier time adding than subtracting. So we're going to take the opposite. We're going to flip the signs on each of the term of the product. When we take the opposite, you flip each of the signs on the terms. All right. So here's what we do. We have a big step here. I encourage you to cross out that product and then write down the opposite. So instead of positive 6x cubed, we have negative 6x cubed. Here, it doesn't really matter, but let's call it minus 0x squared. The positive 2x becomes a negative 2x. I know some students might micromanage and they might do this, minus, minus, minus. I think that looks a little sloppy and confusing. I think it's better if people do this. And remember, the key thing is to be accurate, to get the right answer, and to show correct steps. So when doing your work, I encourage you to do all this. It might seem like additional writing, but remember, you want to get the right answer. It really helps. So when we subtract all of this, we're adding the opposite. I'll do this in green. When we subtract, we're adding the opposite. And once again, you're much better at adding than subtracting. Because at this point, you just have to combine like terms. All these things I've circled in green, you just have to combine like terms now. And that's a lot easier to do than subtracting. Combine like terms. Again, you're much better at adding than subtracting. When you're adding, you're basically combining like terms. All right, 6x cubed and negative 6x cubed, bye-bye. Your result is 0. That was the whole point, right? 6x cubed divided by 3x squared was 2x, okay? And because of all that, we end up with a 0 over here. 3x squared and, well, this thing here is just 3x squared again. A 0x and a negative 2x, that gives a negative 2x. Again, you're much better at adding than subtracting. Because a lot of people, if they try to think, what's 0x minus 2x, it's easy to mess that up. We get negative 2x. Carry down the negative 5. In fact, I might want to extend that line down there. we're combining all the like terms. Don't forget the constant term here. Don't forget the -5. Bring that down as well. So that's why I like to say combine like terms. You don't want to forget the -5. All right. Now, in a way, we can think of this as the new dividend. Think of this as the new dividend. And we basically repeat the process. So we have here, again, 3x squared. Do this in, how about blue? 3x squared is the leading term of the divisor, once again. Look over here. What's the leading term of our new dividend? It's going to be its twin, 3x squared. This should be straightforward. What is 3x squared divided by 3x squared? What's a guy divided by its twin? It's 1. And no, there's no hidden restriction issue here. It's 1. All right? So that's going to be another term we're going to put in the quotient. The positive one goes here in the constant term lineup. All right. So once again, 3x squared goes to 3x squared once in this sense, in this quotient sense. We put the positive one over here as the new term in the quotient. And then what do? We multiply. Once again, we multiply. We multiplied the divisor by the positive one. Of course, when you multiply all of this by positive 1, you're just copying it. All right, so we get the copy. 1 times all this, you just get the copy. 3x squared plus 0x plus 1. Again, the 0x here helps to line things up. If the 0x here helps, great. It helps some students more than others. And again, what do? We've taken the product here. What do with this product? We subtract it now from that dividend. But remember, you're much better at adding than subtracting. When you subtract something, you're adding its what? You're adding its opposite. Add the opposite. So I'm going to cross this out and flip all the signs. Again, some students might just do this, but I think that's a little micromanagey. There we go. I cross this out. Well, I write the opposite first, then I cross it out, because you might cover up some negative signs here. So we write down the opposite, -3x squared minus 0x minus 1, then cross that out. Combine like terms. We're adding the opposite, combine like terms. So we're adding this and this, combine like terms. 3x squared and -3x squared, bye-bye. -2x minus 0x, -2x, we get this guy again. -5 minus 1, hey, you're in Vegas, you lose $5, you lose $1, you've lost $6. Frankly, in Vegas, you're lucky if you only lose $6, but here you go. We end up with -2x minus 6. In a way, that's our new dividend. But I have another name for this thing. Because we're finished with this part of the process. It turns out this will be the what? Back up here, what do we call the 1? We call the 1 the remainder. And I claim that we can call this thing here the remainder. -2x minus 6, this will be the remainder. How do I know I can call this the remainder? Well, what is a remainder? What is acceptable as a remainder? When can we stop this process over here? Well, if we either get a 0 or if we get a polynomial with degree less than the degree of the divisor. All right. What is the degree of the divisor? The degree here was 2. What's the degree of this remainder? Negative 2x minus 6, it's linear. The degree here is 1. And 1 is less than 2. That's very basic math. 1 is less than 2. The degree of the remainder now is less than the degree of the divisor. So this is an appropriate remainder. If this is 0, we're thrilled. But otherwise, we want a polynomial whose remainder is less, whose remainder has a degree that's less than the degree of the divisor. All right, so we're done with this part of the process. And then what do we write? What do we write? Remember what we did over here. The long form was, well, 9 divided by 4 was the quotient 2 plus the remainder over the divisor, right? It was the quotient plus the remainder over the divisor. The quotient plus the remainder over the divisor. 2 plus 1 over 4. Over here, let's do it. What's the quotient? The quotient is going to be, up here is 2x plus 1. That's the quotient. Plus a fraction, because the remainder is not 0. We're going to get a fraction. On the top, we put the remainder, the negative 2x minus 6. On the bottom, we put the divisor, and we can remove the missing term now. 3x squared plus 1. In fact, it's conventional to not have missing terms. Don't put the plus 0x. And we should be good. A quick check. This fraction over here, remember, better be what? I call it bottom heavy by degree. I call it bottom heavy. Because remember, we either get 0 here, if the remainder is 0, or we get a rational expression that is bottom heavy, meaning that the degree of the numerator is less than the degree of the denominator. They cannot even be equal. The degree of the numerator must be strictly less than the degree of the denominator. The degree of the remainder must be less than the degree of the divisor. The degree of the top must be less than the degree of the bottom. All right. We have degree 1 over degree 2. That's good. We get a proper bottom-heavy rational expression. In addition to this quotient. Remember I said in addition. Put that plus sign there. Put that plus sign there. All right. So here's the form, quotient plus remainder over divisor. I just wrote this. And again, to reiterate, don't forget the plus sign. Don't just stick these next to each other. I know with this mixed number, 2 1/4, we put these things next to each other. Don't do that here. You need the plus sign. Or if you don't have a plus sign, what you could do is you can factor a -1 out of the top, and then it becomes a minus sign. But basically, you need either a plus sign or a minus sign over there, all right? Okay, so although I would accept this, since the leading coefficient is negative up here, it's conventional to factor out a -1. So you get the opposite of 2x what? It's the opposite of 2x plus 6. You're flipping both those signs in there. And then you can pop out that -1 factor. So the more conventional way of writing this is the polynomial in descending powers, 2x plus 1. And then when you factor out a -1, the plus changes to a minus. And we have 2x plus 6. That's a plus sign there. 2x plus 6 over 3x squared plus 1. This looks a bit nicer, but I'd accept this as well, personally. All right. We performed the long division. The long division. So when you divide this top polynomial, by this bottom polynomial, you get this result. In other words, you can rewrite this rational expression as this, and we're going to see the impact of that later on. Now you might be asking, is there an easier way to do this? There is if the divisor is very nice, something like x minus 2 or something like that. If you have a very nice divisor, then you might be able to get away with synthetic division. And that's next. Again, up here, watch your signs, right? Also, if there are any common factors on the top and bottom, cancel them out. For example, if you have x as a common factor on the top and the bottom, cancel them out. That's somewhat rare, but it happens sometimes. And watch your signs. All right, once again, next up, if the divisor is very nice like this, you might be able to use synthetic division as an alternative. That's next time.
All right. Any questions? It's a matter of working out the long division, and watch your signs. A very common mistake is to mess up your signs. And remember to put that plus sign at the bottom when you tack on the fraction. Any questions? Any questions? All right. Synthetic.
Hi, everyone. Synthetic division is a shortcut alternative to long division when the divisor is very nice. Something of this form, x minus k. So let's take a numerator, a polynomial f of x in x. And we're dividing it by, let's say, x minus 2. We can then use synthetic division. We're dividing by x minus k, where k is what number? Where k is 2. Now let's say we have a problem like this over here. Our example here, we're dividing f of x, this top guy here, and there's a reason why I'm calling it f of x, by the way. And we're dividing it by x plus 3. Now here, we're dividing by x minus k, where k is what number? Where k is negative 3. So there's a sign flip. Why do we have a minus sign here, and why are we playing this sign flip game? We'll see in just a moment. But again, synthetic division is an alternative to long division where you're dividing a polynomial in x, say, f of x, by something of the form x minus k. So when you write down k, there is a sign flip. This value for k, I'm going to put in a half box. I call it a dunk tank, like at a carnival. Again, if you're dividing by x plus 3, k is negative 3. Because x plus 3 is x minus negative 3. K is negative 3. So here's what we're going to do. I'm going to put negative 3 in the dunk tank, and we're going to take the leading coefficients of f of x, this top polynomial here. And what are the coefficients? Let's be careful. What are the coefficients of f of x in the descending powers form? What's the leading coefficient? The leading coefficient is 2. Now, what's the next coefficient? Now, be careful. When I say the next coefficient, I'm asking for the coefficient of x squared. 2 is the coefficient of x cubed. It's the leading coefficient. But now I want the coefficient for x squared. What's the coefficient on x squared? It's 0 because there's an implied missing term, plus 0x squared. In fact, I am strongly advising that you write down that missing coefficient for the missing term. And then we have, watch your sign, for the x term, the coefficient is negative 3. And for the constant term, it's kind of like x to the 0, right? The coefficient for x to the 0 is 5. It's the constant term. All right. So our first row, when we do the synthetic division, we put the negative 3, the value for k here, in the dunk tank. And then we put the coefficients based on the descending powers form, right? But you must put the 0. You must put that 0 there, corresponding to the missing term. If you put 2, negative 3, 5, that's going to be wrong. you have to put 2, 0, negative 3, 5. You absolutely need this. I don't care who you are. You need it to show your work. Okay, and then we leave the second row blank for now, and then we're going to produce the third row. Now, how do we get the third row? We begin by bringing down the 2. And by the way, this is really a shortcut to the long division. So if you want to know why this works, this is going to seem like magic. If you want to know why this works, work out the long division, and you're going to see the patterns as you work these things out. All right, the 2 comes down. We put a 2 to start off our third row. And then what do we do? Okay, we're going to go on a diagonal from here to here, and we're going to multiply by k, the number in the dunk tank. K is negative 3. What is 2 times negative 3? 2 times negative 3 is negative 6. So we put a negative 6 over here. And then you add down the column. A 0 and a negative 6 is just a negative 6. So remember, you multiply diagonally to get over here in the second row, and then you add down to get the entry in the third row. Repeat the process. What's negative 6 times k, the negative 3? When you multiply by negative 3, I'll write that. When you multiply by negative 3, negative 6 times negative 3 is positive 18. Again, we add down the column. You're in Vegas. You lose 3, you win 18, you're still up 15, positive 15. I know that's joke money in Vegas, but bear with me. Along the diagonal, we multiply by k again. We multiply by the negative 3. I'll put this over here as well. So to get the 18, remember that was negative 6 times negative 3, that gave positive 18. And now we're asking, what's 15 times negative 3? A calculator can help. What is 15 times negative 3? That's a negative 45. Okay, you're in Vegas, you win 5, you've lost 45. Bad hand. You end up with a negative 40 over here. And I'm going to circle that. It turns out this is going to be our value for R. Guess what R stands for? R stands for remainder. Negative 40 is going to be our remainder. So in the end, we care about this bottom row, row number 3. Okay, so when I divide the top polynomial by the bottom polynomial, well, first of all, look at it this way. Think in terms of degrees. We're dividing a third degree polynomial by a first degree polynomial. What degree will the result be? I'll give you a hint here. What is x to the third divided by x, or x to the first? What's x to the third divided by x to the first? It's x to the second. When you divide powers of x, you subtract the exponents. In general, when you divide a third degree polynomial by a first degree polynomial, in general, your result will be second degree. You subtract the degrees. All right. So, see, when you divide the top polynomial by the bottom, what's going to be the leading term of our result, our quotient? Well, third degree divided by first degree gives us second degree. The 2 here is going to be the coefficient for the x squared term. 2x squared. And then the negative 6 will be the coefficient on x, negative 6x, plus the 15 over here. Okay. And then plus, what's the scheme? Remainder, the negative 40, over the divisor, which is way over here, x plus 3. Squeezing that in there. X plus 3. And then you can pop out the minus sign. All right. And you would have gotten this from long division as well. By the way, the remainder has to be a constant because when you're doing synthetic division, we're assuming that the divisor is linear, first degree, which means that the remainder better be a constant, either 0 or something with degree 0. Let's recap the process. All right. Bring down the 2. You multiply by k, negative 6, add down, negative 6. Multiply by k, you get positive 18. Add down, you get 50. Multiply diagonally by negative 3, you get negative 45. Add down, you get negative 40. This is r, the remainder. You use these as the coefficients of your quotient. It's going to be a second degree polynomial. Basically, the degree goes down by 1. When you divide an nth degree polynomial by a first degree polynomial, which is always the case with synthetic division, the result will have degree n minus 1. You drop the degree by 1. All right, so we get, oops, whoa. So we get 2x squared minus 6x plus 15. This is very convenient. Again, if you don't believe me, work out the long division. Okay, plus negative 4 over the divisor, but the negative sign can pop out. Remember, over here, we had plus negative 40 over x plus 3. The minus sign can pop out, so we get minus 40 over x plus 3. If the remainder is negative, it's conventional to pop out the negative 1 factor. So we normally write this as 2x squared minus 6x plus 15 minus the fraction, positive 40 over x plus 3. And this is typically simplified. Again, ideally, this would be what? It would be great if the remainder were what number? It would be great if the remainder were 0. Then we get a polynomial as our result. So remember, a 0 remainder would be great. This would drop off. We just have a polynomial. All right. Next, we're going to talk about the division algorithm and the remainder theorem.
Okay, any questions about the process of synthetic division? It's a matter of getting used to it. And you do need the zeros to the missing term, even more so than long division. You really need them here. Any questions?
Hi, everyone. So before, we used synthetic division to divide this top polynomial, which I'll call f of x, by this bottom polynomial, x plus 3. That's x minus k, where k is negative 3. That's the number we put in the dunk tank. And we got this right-hand side over here. So we claimed that the left side, this fraction, is equivalent to this over here. Let's actually try this out on Desmos. Let's see if Desmos agrees with this. So on the left side, y equals the quantity 2x cubed minus 3x plus 5 all over x plus 3. All right, so we got that over there. Let's see, on the right side, y equals 2x squared minus 6x plus 15 minus 40 over x plus 3. And it looks like we match up. How do you like that? Again, not a proof, but pretty convincing. So it looks like the left side is equivalent to the right side, visually. Now, what's another thing we can do with this statement? Well, we can also write the corresponding division algorithm form. The division algorithm form. That's where we multiply both sides by the divisor, x plus 3. So we're going to multiply both sides by x plus 3. I'll do this in purple or blue. Multiply by x plus 3 on the left, and multiply by x plus 3, all of this. Multiply all of that by x plus 3 on the right. So on the left here, the x plus 3's go bye-bye, and you're left with that numerator, f of x, right? You're left with f of x over here, equals all this times x plus 3. So what happens is you get f of x, the numerator, 2x cubed minus 3x plus 5, equals, I'll put the x plus 3 in front here, times this polynomial, quotient, the quantity 2x squared minus 6x plus 15, minus, and then when you multiply the fraction by its own bottom, you get the top, 40. Just like if you take 2/7 and you multiply by 7, you end up with 2. Likewise here, when you multiply the fraction by its own bottom, you get the top, 40 with a minus in front. That's the division algorithm form. And why is this interesting? All right, now my claim is that the left side is equivalent to the right side, even if x equals -3. Now, some of you might object and go, well, wait a minute, -3 was not in the domain for this fraction or this fraction. Don't worry. By a calculus limit argument, I claim that the left polynomial is equivalent to the right polynomial, even if x is -3. In fact, -3 is the number I want to plug in. So here's my claim. If you plug in x equals -3 on the left, what is that? If this thing is f of x, I'm talking about evaluating f of -3. What happens when you plug in -3 on the left-hand side? You're evaluating f of -3. Equals, well, if you plug in -3 into here, x plus 3, -3 plus 3, guess what? That's 0. And therefore, this times this, 0 times all that, this whole thing is going to be 0. So if you plug -3 into the right side here, this whole product over here drops out, and we're left with this constant term, this remainder, the -40. So let me repeat what I just did. The problem value for x here, which was -3, that was k, right? K was -3. It was the problem value for x down there. If you plug in the problem value for x, that is k, or -3, on the left side, this is f of k then. We're basically evaluating f of k. How can you evaluate f of k? Well, this drops out, and it's just the remainder. F of k equals the remainder, r. F of k equals r. That is the remainder theorem. In a way, it's one of the shortest conclusions in the whole of precalculus. Bottom line, f of k equals r. If you plug the guy in the dunk tank, the problem value for x up here, into the numerator, right? This numerator guy, that's f of x. F of k equals the remainder. So, if I ask you the following, what's the deal? If you have f of x equals 2x cubed minus 3x plus 5, what is f of -3? Now, of course, you could plug -3 into your calculator, but a lot of people would make a mistake because a lot of people have trouble plugging in negative values. And you have a cube and all that. So a lot of people would mess this up, actually, even on their calculators. But there's an alternative. You can use synthetic division. You can use synthetic division to evaluate functions, namely at x equals k. F of x equals ya. You want to know what f of negative 3 is. What can you do? Well, you do the synthetic division. You plug negative 3 into the dunk tank, all right, work out the synthetic division, and this remainder here is the answer, negative 40. So I claim that f of negative 3 is negative 40. If f of x is the numerator, the dividend, f of this, f of k equals this, r. f of k equals r. f of negative 3 equals negative 40. So there are two reasons why you would want to make this table. One, if you wanted to evaluate f of negative 3, where this was f of x, or if you wanted to divide f of x by x minus k. Now remember, if you're dividing f of x by x plus 3, there's a sign flip. If you're dividing x by x plus 3, remember there's a sign flip, and you actually want to put k equals negative 3 in the dunk tank, like so. So if you're dividing by x plus 3, there's a sign flip, you put negative 3 in the dunk tank. But if you're evaluating f of negative 3, there's no sign flip. Do not flip the sign. There's no sign flip if you're evaluating a function. All right. Now, where do you evaluate functions? Anytime you want a y coordinate. So for example, let's go over to Desmos over here, all right? Let's go to a new screen here for Desmos. All right, now let's look at y equals the numerator, the dividend. So let's consider the graph of y equals 2x cubed minus 3x plus 5. It's this snake. Let's say that I care about when x is negative 3. I want to know the intersection point between these two graphs, the red and the blue. Okay, now it might help if I change the window. All right, so let's make the x go from negative 5 to 5. All right. Okay, so unequal scales, that's okay. Well, actually, it works out very nicely. You can tell right now it's going to be negative 3, comma, look at this, negative 40. So I want to know the point on this red graph that has x coordinate negative 3. What's the function value at negative 3? What's the y coordinate? F of negative 3 is, lo and behold, negative 40. That's the y coordinate at this point. So you might actually want to play this game in calculus. For example, what if you have a max point up here? Let's say you know its x coordinate is negative 3. You can use synthetic division and find the y coordinate. You can use, in fact, when I talk calculus, students would do this. They'd use synthetic division to find y coordinates. It's very convenient. And you can use synthetic division. For a lot of people, the synthetic division is faster than if you were to actually plug into a calculator. This is faster and more accurate than if you were to plug into a calculator. Because with this, it's just bring down, multiply, add, multiply, add, multiply, add. That's more straightforward and more accurate and harder to mess up for a lot of people compared to if you tried to take this guy and plug in negative 3 on a calculator. A lot of people would mess that up. Next up, how is this all related to polynomial theory? Zeros, factoring, and division. Next time.
Any questions? Any questions? I guess this one didn't caption. All right.
Hi, everyone. A key theme of Chapter 2 is factoring polynomials. When you factor, you do a D word. You divide. And what's one of the purposes of factoring polynomials? So you can find their zeros. So these are all connected. And this is why polynomial division has been the subject of section 2.3. All right, let's get right to it. Let's say that we have f of x equals 4x cubed minus 5x squared minus 7x plus 2. We've seen this before, actually. Now, let's say that a little bird flies in and whispers to you, psst, tweet, tweet. 2 is a 0 of this polynomial function. Now, let's say we believe the bird. Later on, we won't need the bird. Then you can eat it, unless you're vegan. But let's assume that the bird is right. Let's assume that 2 is a 0. Of this polynomial function in x. Well, then by the factor theorem, remember the factor theorem, if 2 is a 0, then what must be a factor? X what? X minus 2. If 2 is a 0 of this polynomial in x, then x minus 2 must be a factor. Right? Meaning that f of x can be written as such. F of x equals the factor x minus 2 times another factor. And how do we get this other factor? When we factor, we do what D word? We divide. When we factor, we divide. So the other factor here is obtained by taking f of x and dividing by x minus 2. Just as if I were to ask you, 10 is 2 times what? 10 is 2 times 5, because 5 is 10 divided by 2. So in order to get this other factor, we have to divide f of x by x minus 2. Sound familiar? What's a way that we can do this really fast? Synthetic division, where k is what number? We're dividing by x minus k, where k is 2. There's a sign flip. We're dividing by x minus 2, so k is positive 2. That's the number we put in the dunk tank. We want to work this out. We put 2 in the dunk tank. We take the coefficients. Notice this is in descending powers. There are no missing terms. The coefficients are 4, negative 5, negative 7, 2. Work out the synthetic division. Go. I'll give you 30 seconds. All right. We bring down the 4. 4 times 2 is 8. We multiply by k. K is 2. We add down. Negative 5 plus 8 is 3. 3 times 2 is 6. Negative 7 plus 6 is negative 1. Negative 1 times 2 is negative 2. And finally, 2 plus negative 2 is 0. Ah, look at this. What's 0? It's the remainder, r. What does the remainder theorem say? The remainder theorem says that f of k equals r. In this case, it says that f of 2 equals 0. That verifies that 2 is a 0 of the function. So the bird is correct. The bird is correct. All right, 2 is a 0, and therefore we can conclude all this. All right. So what is this other factor? What is this other factor? Well, look at these coefficients here. We start off with a third degree polynomial. A third degree, this is degree 3, over a first degree, this is degree 1, gives what degree? Degree 2. We know that this has to be second degree. So what's the other factor here? It's going to be given by 4x squared plus 3x minus 1 with a 0 remainder. We get a polynomial quotient here. 4x squared plus 3x minus 1. There we go. 4x squared plus 3x minus 1. And since there was no fraction, the remainder was 0, there's no fraction in here, we have a nice clean partial factorization. This is factoring. We factored this third degree polynomial here into a linear first degree polynomial times a second degree quadratic polynomial. It's a QD, a quadratic trinomial. But we're not done yet. We're not done yet, okay? Because we can factor this further. By the way, remember, we love it that the remainder here is 0. That means that the quotient's a nice polynomial, and we have a partial factoring here. But we can factor it even further. Okay, so using old school factoring, the QD turns out to be the factor 4x minus 1 times the factor x plus 1 in either order. And then from here, we can get all the real zeros, all the real zeros. Set these equal to 0, solve. What are the real zeros? They turn out to be positive 2. From here, set this equal to 0, solve for x. You get 1/4. From here, you get negative 1. Now, these are the zeros of the function. These are the zeros of f of x. The real zeros of the function correspond to what points on the graph? The real zeros of the function correspond to the x-intercepts on the graph. 2, 0, 1/4, 0, and negative 1, 0. In fact, we can sketch a graph of this thing. Remember, the leading term up here was 4x cubed, all right? That's the dominant or leading term. How do you graph y equals 4x cubed? What was the long run behavior, which shares the long run behavior of this, basically? Y equals 4x cubed, that's a rising snake. It's going to go up, up this way, and down, down this way to the left. Up, up to the right, down, down to the left. All right, so from left to right, we're coming up from hell. Now, the first x-intercept we run into is this fellow, negative 1, 0. Graph comes up. We hit this point. And because all the exponents here are 1s, the multiplicities are all 1s, each with multiplicity 1, which means that the graph does what at each of these x-intercepts? 1 is odd, so that means the graph cuts like a snake at each of these x-intercepts. By the way, what's the y-intercept? What was the constant term up here? The constant term was 2, so 0, 2 is going to be our y-intercept. And then I don't know where it peaks, okay? But I do know that there's an x-intercept at 1/4. If I had to bet, I would bet that it peaks before that, but let's see what happens. All right, we cut again because the multiplicity is 1, odd. We cut again. There's some sort of minimum point down here. In calculus, we can find out where it is by setting the derivative equal to 0. We're going to come back up until we hit 2, 0. That's our last x-intercept. The graph cuts again and shoots up, up, up. Okay. Here's a nicer picture, right? x-intercepts at -1, 0, 1/4, 0, and 2, 0. It turns out that the peak was in quadrant 2. You can verify that with calculus. That's where the derivative is 0. And we have a minimum point here in quadrant 4, of course. Again, you can locate that using calculus, where the derivative is 0. Here's an even nicer graph. Let's go to Desmos. Here's an even nicer graph. All right. Y equals 4x cubed minus 5x squared minus 7x plus 2. Let's verify that our factorization was correct, by the way. We claimed the factorization was y equals x minus 2, and then 4x minus 1, and then x plus 1. There you go. Looks like a match. What happens? We have an x-intercept at -1, 0. There's a cut there. We have an x-intercept at 1/4, 0. Oops. 1/4, 0. There's a cut there. And an x-intercept at 2, 0. There's a cut there. Right. There's a y-intercept at 0, 2 from the constant term. Overall, it's a rising snake. We know a lot about this guy. The only thing we don't know yet are where exactly the max point is and the min point. But you can find those in calculus. You set the derivative equal to 0 and then find out where the y coordinates are. Maybe it was Untitled Division. All right, so we know a lot. We've graphed that cubic to a good extent. All right, y equals this. We've graphed that cubic to a good extent. All right, next up, we've talked about real zeros of a function corresponding to x-intercepts. What about the imaginary zeros?
Okay, so that's 2.3. It's such a good time for a break. Remember, we have questions later today. So let's go ahead and take a break until 8:23. All right. We're going to mute and I'll record. All right. Any questions right now? I'll see you in about 10 minutes. All right. And we'll do imaginary numbers. All right. Any questions before we go on? We'll do a bit of imaginary numbers, complex numbers, then we'll take questions. Start around 8:45 or so. So we're no longer keeping it real, which reminds me of one of my favorite comedians. Let's see. This one here. Yeah. This is a pretty well-known meme. Don't think there's a copyright there. All right. So let's proceed. Let's talk about imaginary numbers.
Next time. There we go. Hi, everyone. This was our Venn diagram from back in section 0.1 for sets of numbers. So far, we've been keeping it real. But now we're going to extend to the broader set of complex numbers, C, where we're going to throw in the imaginary numbers, such as I. Later on, we're going to talk about the complex zeros of a polynomial function, which could be real or imaginary. Section 2.4 is on complex numbers in general. Now, -1 has two square roots, called I and -I. I is the principal square root of -1, and we call I the imaginary unit. I squared is therefore -1 itself, and that's something that you use a lot. Now, when you simplify radicals, such as these, you need to make sure that the new radicand becomes non-negative. So, for example, the principal square root of -15 is written as I root 15. If you want, you could write this as root 15 times I, but what's the danger? A lot of students extend the radical too far and put it over the I, which would be wrong. You're not supposed to do that. So if you're afraid of doing something like that, then it might be better for you to just put the I out in front. Root negative 16 is I times root 16, or just 4I. Root negative 18 is I times root 18. And then old school, root 18, because 9 divides 18, and root 9 is 3, basically the 9 comes out of the 18 as a 3, and the 2 stays behind. Again, 18 is 9 times 2. The 9 comes out as a 3. We have 3 root 2. That's I times 3 root 2, or 3I times root 2. Again, it might be safer to put the radical at the right end. Standard form for a complex number. Something like 2 plus 3I is an imaginary number written in standard form. A is the real part, which is 2 here. B, or BI, is the imaginary part, which is 3 or 3I over here. Standard form is A plus BI, where A and B are real numbers, and one or both could be 0. Again, C is the set of all complex numbers, and every real number is a complex number. R is a subset of C. Every real number is also a complex number. So even numbers like 7 or 0 are also complex numbers. So all of these are complex numbers. 2 is an integer. In fact, it's a real number. That's also a complex number. 3i over here is a pure imaginary number because the real part is 0, and it's not 0 itself. 2 plus 3i is another imaginary number. Over here. All right. Now, the real number line represents the set of real numbers. If you have 2 distinct real numbers, like -1 and pi, we know that one has to be greater, one has to be lesser. But what if you have 2 imaginary numbers, like 2 plus 7i versus 4 plus 5i, which is greater, which is lesser? It's kind of hard to say. There's no such linear ordering like for the real numbers. Instead of a real number line, we represent the set of complex numbers using the complex plane. So if we want to plot a number like 3 minus 4i, we're basically plotting the ordered pair 3 comma negative 4 in the complex plane, a comma b, where a is the real part, b is the imaginary part. So 3 is on the real axis, -4 is on the imaginary axis. These take the place of the x and y axes. And here's 3 minus 4i. Every point here corresponds to a complex number, including 0 over here. Next up, we're going to discuss powers of I and how to simplify them.
Okay, let me adjust a few things here. We're starting questions about 845. Okay, any questions before we go on? Any questions before we go on? All right, we're just, okay, so we're doing 2-3 and we're just barely starting 2-4 today. All right.
Hi, everyone. You often see these on placement exams, simplifying powers of I. So for example, I to the 0 is 1, just as 2 to the 0 is 1, and 3 to the 0 is 1. I to the first is I. A horse is a horse. I to the second, remember, I squared, is -1. And I to the fourth, sorry, I to the third, I to the third is I to the second times I to the first. I to the second is negative 1. I to the first is I. Negative 1 times I is negative I. So if you memorize these 4 basic powers of I, you're really in business. Because take a look here. What's I to the fourth? I to the fourth is the square of I squared. What's I squared? I squared is negative 1, and the square of negative 1 is positive 1. So here, I to the 0 is 1. Now we're back to I to the fourth being 1. Now remember, every time you increase the exponent by 1, you're multiplying by I. At each step, you're multiplying by I. So I to the fourth times I will get you I to the fifth. Well, it follows this pattern. 1 times I is I times I is negative 1, negative 1 times I is negative I times I takes you back to 1. You're going to cycle around. 1, I, negative 1, negative I, and so forth. They're going to keep cycling around.
Okay, now before I get to the picture, I want to show you something. It's another game show. Take a look at this. Again, you don't care about how many times the wheel goes around. You care where you stop. It's not the integer number of revolutions. You care about the remainder, where you stop, not the quotient.
It's like following this wheel. In fact, in general, if you take a complex number, plot its point, and if you multiply it by I, that means you take the point and you rotate it 90 degrees clockwise about the origin, or 0. So remember, folks, I to the 0 is 1. I to the first is I to the second is negative 1. I to the third is negative I. And then back here, I to the fourth is 1. Keep going. I to the fifth is I again. I to the sixth is negative 1 again. I to the seventh is negative I again. And I to the eighth is 1 again. We go around this wheel. Now, when you go around this wheel, let's say I want to simplify I to the whatever, any positive integer, I to the whatever. So what's the deal? It's not that I care how many times I spin around here. It depends on where I land. So what's the deal? Let's look at I to the 100. It's similar to these guys. What do all these exponents have in common? 0, 4, 8, 100, and so forth. They're all divisible by 4. So if the exponent is divisible by 4, you're going to end up with 1. All of these are equal to 1. That's how they simplify. So you end up with 1 if you get a remainder of 0 when you divide the exponent by 4. So that's the idea. You take these non-negative integer exponents. When you divide them by 4, you look at the remainder. If the remainder is 0, these are all equal to I to the 0, or just 1. Remember, it's really key that you remember this leftmost column here. I to the 0 is 1, I to the first is I to the second is negative 1, I to the third is negative I. And then with the rule we're going to develop, these are all you have to remember. Over here, for I, what's true of these exponents? 1, 5, 9. When you divide by 4, what happens? The remainder here is always 1. Over here, whoops. Over here, I to the second, 6th, 10th, and so forth. When you divide by 4, the remainder is 2. Over here, I to the 3rd, 7th, 11th. When you divide by 4, the remainder is 3. So for example, I to the 0, when we divide 100 by 4, well, you get 0 as the remainder. I to the 0 is 1. Now 100 is 25 times 4. So that means we spin around 25 full revolutions, but we don't care about that. We don't care about that. We only care that the remainder is 0. You end up at that starting point, at 1. Right. How about I to the 83rd? What's the remainder when you divide by 4? Well, bear in mind that 80 is divisible by 4. 83 is 3 more than that. So that's one way to look at it. You know that I to the 80th is going to be 1 because 80 is a multiple of 4. The remainder for this guy is 0. And then you walk 3 more steps. 1, 2, 3. And you end up at negative I. I to the 83rd is I to the 3rd, and you better remember that that's negative I. I to the 83rd simplifies to negative I. Right. So once again, I to the n, where n is a positive integer or non-negative integer, if you include 0. I to the n equals I to the remainder when n is divided by 4. I know the exponent is very long here, but I to the remainder when n is divided by 4. And then you can fall back on this basic list. And your final answer will either be 1 or I or negative 1 or negative I. Right. Remember, I to the 100th is 1, so is I to the 1000th, and so forth. That's good to remember. Next, how do you add, subtract, and multiply complex numbers?
Okay, so just a couple more minutes. Any questions? Just a couple more minutes here, and then we'll start the questions. All right. And by the way, after this part, do I have it? Okay, I'll double check. Okay, but you can do like was it number 8? You can do only sum of 2.4 after this.
Hi everyone. Let's add, subtract, and multiply complex numbers. Division's harder. First, simplify all the radicals. Think of I as x, and then add, subtract, and multiply as usual. But then simplify all powers of I. For example, I squared is negative 1. And then get it down to standard form, like 2 plus 3i. All right. Example, simplify this. The principal square root of negative 9 times the principal square root of negative 4. Now remember, the product rule does not apply. The product rules does not apply. So it is inappropriate to say, oh, multiply these radicands, and then root 36 is 6. That's not going to work here. You first have to simplify the radicals. The principal square root of negative 9 is 3i. The principal square root of negative 4 is what? 2i. All right. 3i times 2i is 6i squared, but we're not done yet. I squared is what? I squared is negative 1. Make sure you indicate that's a product here. And then 6 times negative 1 is negative 6. Bear in mind, you can skip this step. You go straight from here to here. 6i squared is negative 6. When you multiply by I squared, you're taking the opposite. And you can do that immediately. Notice that this is not positive 6, which you would have gotten if you had incorrectly applied the product rule. Remember, the product rule for radicals applies if the radicands are non-negative, not if they're negative. All right. Next, simplify. When you multiply the complex number 2 plus 3i by the complex number 4 plus I, what complex number do you get as the product? Well, think of I as x, and then FOIL, that is distribute. Right? So 2 times 4 is 8. 2 times I is 2i. 3i times 4 is 12i. And 3i times I is 3i squared. And you put these together, FOIL. 8 plus 2i plus 12i plus 3i squared. Well, what's 2i plus 12i? That's 14i. Just like 2x plus 12x is 14x. What's 3i squared? That's 3 times -1 or -3. Let's just consider that as -3. So we have 8 plus 14i minus 3. Finally, 8 minus 3 is 5. We put the real part in front on the left of the standard form. We get 5 plus 14i. Of course, this is not 19i. The 14 is married to the I. So that times that is that as a complex number. Division is harder. That's next.
All right, so that's all for that. Okay, let me go double check here. Well, okay, I forgot this number 8, but you can go through part of 2.4. So here's the plan. Okay, so here's the plan. Keep going to chat. Okay, so gather your thoughts, gather your questions. 8:50. Let's start questions. I'll give you 5 minutes to gather your thoughts. You can put some ideas, some numbers in chat. Okay, I'll give you 5 minutes to prepare yourself. Okay. And 8:50 will start the session. All right. Okay, so I'm keep recording. All right. Okay, so let's start. Okay, so let's start to get through here. All right. So I'll just go down the list. Okay, 1.6, number 4. Oh yeah, the decomposition problems. All right. Okay, so I'll go through these. All right. So we want u or g of x to be the inside function, right? So basically on A, you want g of x to be the inside guy. That's probably the radicand, x squared minus 7. Most people choose the radicand. Okay. And then for the outer function, y or f of u. So what do we do to this inner guy? We're taking his cube root. All right. And then one way to check this is that you can plug this thing for u, plug it in, and see if you get the original, and we do. All right. And then it's similar for the other two. You have the answers in the answer sheets, but the idea is that on here, you let g of x or u be the base. Over here, I might recommend u to be the denominator. Something that's hard to reach, something that you'd love to replace with a u. And then f of u here would be 5 over u. F of u here would be u the 8th. Right. Okay, so that's 1.6 number 4. Let me know if I need to elaborate on that. Okay. See, 1.10 number 5. Okay, by the way, we're still recording. Let me know if you want me to stop. All right. Number 5? Okay. Right, I think this is one that we just barely started at the end of Tuesday. I think we did number 4 on Tuesday, so I'll do this one now. All right. Now remember, when you see something like this, you're thinking what S word? You're thinking, I hope, substitution. So if f of x is root x, f takes the square root of its input. What's f of x plus h? Is it this? Square root of x all plus h? That's tempting, but the answer is no. You have to substitute. So it goes the square root of x plus h minus f of x over here is root x all over h. Okay, so that's part of the battle right there. All right, so then you take this and you're going to rationalize the numerator. How do you rationalize the numerator? How do you rationalize the numerator? You multiply top and bottom by what?
Conjugate.
Right, conjugate. Okay. For good measure, I'll put parentheses. Not necessary, but it's good to orient yourselves. All right, conjugate is root. Again, you don't need the parentheses, but I think it helps. Root x plus h plus root x. Got to be fair. Divide by the twin. Because we're multiplying by 1. Don't worry about domain issues right now. All right, let me know if you have any questions. Any questions so far? All right. Okay, now what's the rule that we're going to apply here? We're going to apply the rule that, let's see, if you have the quantity a minus b times the quantity a plus b, right? That's a factorization for what? It's the factorization for a squared minus b squared. It's the factorization for the difference of two squares. So for this here, we're going to get the square of the first radical, the square of root x plus h minus the square root x. Okay, all over that ugly denominator of the h, and don't forget the bottom right. Sometimes I forget the bottom right. Wishful thinking. H times the quantity, root x plus h plus root x. Over here, what's the square of root x? Assume x is non-negative. What's the square of root x? That's x. I'll put this in parentheses, but you don't really need it until you get two or more terms, like if these were switched. What's the square of root x plus h? That's x plus h over the same denominator. Any questions? All right. What's x plus h minus x? Goodbye. Goodbye. Now, you should write more than I am. I'm giving you the sketch here. So you get h over h times the quantity root x plus h plus root x. And then what can we do? What can we do? H divided by h is 1. So you end up with 1 over, don't forget 1 over root x plus h plus root x, where h is not 0, but we're not messing with domain anyway. All right. Any questions? Any questions? To find the derivative, you let h approach 0, and you get 1 over 2 root x. That's the derivative of the square root function. That's 1.11. That was optional. All right. All right. So let's see. Okay, 1.5, number 3. Oh, round down. Okay, so these are just round down. When you round down 2.3, it's 2. So here's 2.3. What's the closest integer without going over? It's 2. You're rounding down. You're rounding down. Round down 5.7. What do you get? Round down 5.7. You get 5. It's not 6. 6 is going over. 5. When you round down an integer, it's the integer. -4. Over here, what's the closest integer without going over? -6 is going over. You don't want him. You want -7. All right, any questions? Okay, let me, do I have the, I have so much here. Do I have the answers over here? I need the B answers. Hold on. What is this? Okay, I do have that. Okay. All right, 1.10. See, 1.5. 25 -4.9%. Right. Okay. All right. -1.10 number 3. Average velocity. All right. Over here. Okay, so for average velocity, we're looking at the average velocity between here and here. All right. So it's going to be S of 4 minus S of 0 over 4 minus 0. S of 4 is 0 minus S of 0 is 256. I'll divide by 4. Is that 64? -64. Careful, watch the sign. -64. Okay, because decreasing slope. Negative slope. Negative slope. It's decreasing negative slope. So that's -64. Unit of height is what? Feet. Unit of time, t, is seconds. Feet per second. Yeah, -64 feet per second. All right. Oh, on 1.3. Well, the proofs would require some knowledge, right? You'd work out the proofs. So 1.3 would give the proofs. And then just from the even or odd properties, or if they're neither, you can state the type of symmetry. And 3 or 4 just offer an explanation. It should just take a few words, right? Okay. All right, 1.5. Okay. The graph. All right. Did I do 3 yet? Yeah, I did. Okay. So 2e.
Sorry, can you show 1.10 number 3 again, please?
10 number 3. Was it the... I put that up here. Do you understand this? It's the average rate of change. It's average velocity.
Where do you get 0? 0, the second,
0 here.
0 minus 2, okay.
We want to know the average, is the average velocity between the time it's dropped and the time it's the ground, right? So that's between times 0 and 4. Yeah, between the time it's dropped and time it hits the ground. That's between time 0 seconds and 4 seconds, right? Okay, any questions about that? Any more questions about this, the average velocity? It's S of B minus S of A all over B minus A. All right, negative 64 feet per second. It's negative because it's sloping downward.
Isn't velocity always positive since it's just like a vector?
No, you're thinking speed. Velocity is here because the coin's dropping. So whether you have average or instantaneous velocity, it's always going to be negative if the object is dropping. Velocity can be negative. Speed is the absolute value of velocity. Speed is never negative. Velocity can be negative. It means you're going in the downward direction.
All right. And I was actually doing this problem today. And since we had to refer back to the problem with the equation 256 minus 16t squared, how do we get this negative 16 there?
Well, that comes from. Are you wondering how the formulas, where the formula comes from? It comes from the fact that g, the gravitational constant for Earth, is negative 32 feet per second per second. It's a measure of acceleration. Is that the question? Where the negative 16 came from?
Yeah.
Yeah. You're solving a second order differential equation where the gravitational constant of acceleration is negative 32 feet per second per second.
Okay. And why is it halved?
It's from the integration. Yeah, you don't know that.
Okay.
It's from the integration.
Okay.
Right. The integral of negative 32 is negative 32t plus c. The integral of that is negative 16t squared plus ct plus d.
Got it. Thank you.
Okay, 1.52e. Okay, graph. Graph. Okay, how do you graph y equals 2? Y equals 2 is a horizontal straight line. But you stop right before -1, x equals -1. Okay, so you have an open endpoint there. That takes care of the first rule. For the second rule, you have y equals 3x plus 1. All right. And it goes from -1 to 0. Okay, that's where we work out the endpoints. All right. So over here, x equals -1, x equals 0. All right. Now, when you plug in, you're going to find the endpoints. Uh, um, all right. 3 times -1 plus 1. All right. So that's going to be -2, right? Okay. So x equals -1, y equals -2. That's an endpoint. Because of the bar there, it's included. Okay. Plug in x equals 0. 3 times 0 plus 1. That's going to be 1. All right. Let's see. X equals 0. Y equals 1. Because of the lack of a bar there, that's a strict inequality. This point's excluded. All right. 3x plus 1 is a piece of a line. Left endpoint's at -1, comma, -2. All right. And then going up to 0, comma 1, 0, comma 1 up here, right? Excluded. Slope 3, rise 1, 2, 3. All right. Run is 1. All right. So that should be the piece of the slanted barbell, y equals 3x plus 1, that you graph as your second piece. Third, y equals x squared minus 2. All right, 2 endpoints, x equals 1, x equals 3. Okay, so you're playing to x squared minus 2. Negative 1. 1 minus 2 is negative 1. Okay, so x equals 1. Y equals negative 1. And that's included because of the bar. Weak inequality. X equals 3. 3 squared minus 2 is 7. 9 minus 2 is 7. The point 3, 7, because that's we have bars at both of the endpoints, so both the endpoints are included. So up here, 1 negative 1 is included. Notice it's still past the VLT. See where we see. 1 negative 1 is included. That's over here. We're still past the VLT. And then 3, 7 included. Okay, not the scale, but 3, 7 is way up here. Okay, that's included. All right. Oh, wait, this is 1 negative 1. Right, okay, 1 negative 1. Y equals x squared minus 2. That normally has a y-intercept at 0, comma, negative 2. We're getting the upslope. Okay, and then it turns out this is 0 at root 2, which is about 1.4, but that's kind of hard to trace. But something like that. All right. Yeah, that's right. That's right. All right. Any questions? Any questions? Well, yeah, it's true that domain and range, if you know the domain and range, that can help you. Well, it depends what the nature of the function is. Okay, so Nick, that was a lot. I mean, do you have any questions about the piecewise function?
No, I got it. I didn't know that you're supposed to just plug in that number and solve for the y coordinate. I don't know why my brain just wasn't working when I was doing those.
Yeah, so
But
you need to
I
remember.
understand it now. It makes perfect sense.
Yeah, yeah, and the thing is, sometimes the endpoint's excluded. So if you see So if you see the strict inequality, if there's a lack of a bar, you just have to remember that, like here and here, you just have to remember that you're going to exclude the endpoint. Okay, but you still plug it in because you want to know it's a limit issue, right? What point are you approaching? All right. So let's look at 1.10 number 4.
Sorry, can you help me explain just real quick why on 2b on those why -2,
Wait, which section are you on?
the one that we just did, but it's b.
B on this one?
Yeah, like I just don't understand how when I plugged in -1 into 3x plus 1, how -1 is, or -2. I just don't get it. I don't understand how that doesn't work.
3 times -1 plus 1 is -3 plus 1 or -2. That's the answer, right?
Yeah.
Right.
Oh my god.
So -1 is just
That's
barely.
why. I just honestly thought, I don't know why I mixed it up. 2 and 1. That's why.
Yeah, and it's just barely in the domain, but does count, right? All right. Okay. Okay, what's next? 110 number 4? Oh, 110 number 4, look at the Tuesday video. And we can refer back to it if you have time. 110 number 4, look at the Tuesday video on YouTube. Okay, 199. Oh yeah, I just discussed it here with somebody. Oh yeah, it was during office hours. I discussed it with somebody in office hours. I kept my notes here. All right. So basically here, I'm telling you that it's a linear conversion rule. It's a linear function rule that converts you from Celsius to Fahrenheit. Because f of 0 is 32, and because f of 100 is 212, that means that the point 0, 32 is on the graph, the point 100, 212 is on the graph. So basically, you want to find slope-intercept form, y equals mx plus b, where you find the slope, rise over run, that's from these 2 points, okay? And then the b is 32, because that's the y-intercept. There's a point with x equals 0, b equals 2, and it so happens that what was I going to say? Yeah, b is 32, because it corresponds to the y-intercept. So slope-intercept form is y equals mx plus b. You know b is 32. You find the slope is rise over run. Now in B, it's very similar, except that instead of 0, 32, it's 32, 0, right? Remember the values are switched. And instead of 212, 100, instead of 100, 212, it's 212, 100. But it's the same basic idea. You have to compute the slope and then find some way to find the slope intercept. You can do that by either plugging in one of these values and solving for B, right? There may be other ways of doing it. Okay, what's next? 1.2 number 6. Yeah, it's hard for me to keep track of these things, but 1.2 number 6. Oh. Okay, h of r equals 9 minus r to the 4th. Use your graph from exercise 1 to determine the intervals of increase and decrease. Oh, yeah, okay. So the graph, I'll just show you the answer to the graph. Okay, so here's the graph, right? So just going on here, the function is increasing on the interval from negative infinity up to 0, bracket. You normally claim as much as you're allowed to. Because remember, technically, you're only supposed to be talking about a function increasing or decreasing on intervals. So here, the function is increasing on the non-positive reals from negative infinity towards 0, all right? And it's decreasing on 0, comma, oops, infinity. So this function is increasing on the set of non-positive reals from negative infinity to 0, and it's decreasing on the non-negative reals from 0 on, up this way, down that way. Wait, what? 1, 2, 6, and then 7i and 7j. All right. Okay, so let's see, 1.27i 7j. All right, these here, right? From the time it was dropped, how long did it take for the coin to be 100 feet above the ground? Okay, so you're asking, when's the height equal to 100? So the idea here is that you take the 100 feet, plug into there, and solve for t. That's the idea. 100 equals this over here, solve for t. Subtract the 256, divide by negative 16, and so forth. Let me know if you want me to write that out, but that's the idea. You plug 100 into the left-hand side, and then you solve for t. For j, verify your answer to e by solving an equation. Verify your answer to e. From the time it was dropped, how long did it take for the coin to hit the ground? All right. Well, from the figure, no. Is it from here? Yeah. So the coin's hitting the ground at time 4 seconds. So you want to show that's the time of impact. Yeah. All right, so you want to know when the height is 0. 0 equals negative 16 t squared plus 256. Basically, you solve that for t, where t is assumed positive. Okay, so yeah, I don't know if people are getting this. So let me know if you have any questions. Okay. By the way, it's 9:31, but I'll go on a bit. We just did number 4, right? We just did 164. Wait, what's going on? Is that a repeat? Yeah, 164 is a repeat. All right. Oh, by the way, 133 is because it's not symmetric, right? Right. This is not even because the graph is not symmetric about the h-axis. It's a domain problem. The domain is not symmetric about 0. If the domain is not symmetric about 0, there's no way it can be an even function. Ugh. All right. Okay, 110, 2 to 5. Oh, wait a minute. Okay. So let me explain this. So with 1.10, 2 and 3 refer to the formula. Basically something like this, right? A difference quotient. Okay, so 3 I already answered, right? 3 I did before. 4 I answered on Tuesday, and 5 I just did. Okay, so if you have any particular questions about those, let me know if you have particular questions. But otherwise, number 2, you apply a formula like this. Number 3 we just did. Number 4 we did Tuesday. Number 5 I just did. Okay, 1.9 number 8. Okay. You're finding the inverse, right? So on this one here, the original was y equals 2 times the cube root of 4 minus 5. All right. Okay, y equals 2 times the cube root of 4x minus 5. All right. So the first step is to replace g of x with y. Second step is to switch x and y. So x equals 2 times the cube root of 4y minus 5. Okay. So we're switching x and y. 3, you're solving for y. Start by dividing by 2. Okay. So x over 2 equals the cube root of 4y minus 5. All right. What then does a cube root? What then does a cube root? Cubing. And then what can we do to both sides to help isolate 4y? Add 5. X over 2. All cubed. Okay. So x over 2 all cubed plus 5 equals 4y. All right. And then divide both sides by 4. And, oh, okay. All right. So working this out, we get y on here equals the cube of x over 2 is x cubed over 80, x cubed over 8 plus 5 okay, all over 4. Okay, now the problem is that we have here a compound fraction, all right? How can we clear the compound fraction? Multiply top and bottom by 8. All right. So when we do that, when we distribute on the top, we get x cubed plus 40 all over 32. And that's going to be f inverse of x. We have to do this because we don't want a compound fraction as our final answer. All right, 8 times, wait. Yeah, 8 cubed, x cubed plus 40 over 32, right. And what is this? This is f inverse of x. All right. Now where are we? Okay, 161E.
I'm not sure if you're doing the rest of the question, but after that, you just have to find g of x. I mean, g of 6.
You plug in 6, right? Where's that? Where's that?
The G inverse of 6.
198. Yeah, you plug in 6. So 6 cubed is what? 216 plus 40 is 256 over 32.
Yes.
26 over 32. That sounds familiar.
It's 8.
It's 8. Yeah. Yeah, it's 8. You plug 6 into here. Okay. Let's see. Yeah, I'm getting lost with all the questions. 4.
We're on 1.10, number 6.
Let's see here. Okay, right. Okay, because 4 I did Tuesday, 5 I just did, 6 is the last difference quotient. All right. Is that where we are? 198? Yeah, we just 198 and 110.6. All right. Okay, so once again, G of t plus h, what S word are you thinking? You're thinking substitution. All right. And this is similar to the problem in the notes. All right, so that difference quotient over there is going to be, I'll get straight to the point. All right. 5 times t plus h squared plus 3 times the quantity t plus h minus 2. Minus. So G of t is the group 5t squared plus 3t minus 2. Make sure you put grouping symbols here. Five t squared. All right. All over h. Okay, that's where you start. That's the key thing to do the substitutions. All right. Did anyone have trouble working this through? Did anyone have trouble working this through? Okay, so I'll just leave this up for now. All right. But keep working that through. One 4-6b. Oh yeah, yeah. Okay. So 146b. Actually, I think I discussed this on Tuesday. So check the video on Tuesday. But the bottom line is that we don't know very much. Because here's the deal. 6 is telling us that we have x-intercepts at 3, 0, and 9, 0. What impact does this have? It raises the graph up 1 unit. But where are the new x-intercepts? We don't know. We don't know what sharks are 1 meter below the ocean. I only know that 3, -1 and 9, -1 were not on the old graph, because otherwise we'd fail the VLT. So the bottom line is that we don't know much about the new zeros of the new transformed function, except for the fact that 3 and 9 are not zeros. You cannot have the same zeros as before because the graph has to pass VLT. Yeah. Okay. Now 1.11, remember, those were optional problems. And the idea is that basically you take the results here and you let h approach 0. So for 4, 5, and 6, you should have had an expression. You should have ended up with an expression with h in it. You let h approach 0. That is, you replace h with 0, and you see what result you can get.
So just replace h with 0 after the equation is all set up?
Right. So when you work out 4, 5, and 6, you're going to get an expression with an h in it. In 1.11, you take the limit of the difference quotient as h approaches 0. So the way it works out is that you just basically plug in 0 for h and simplify.
And this carries over for a, b, and c?
Right. That is for a, b, and c. You set h equal to 0, and you simplify the expression.
Got it. Thank you.
Okay. Is this 1.10 number 2? I remember. Yeah, that was one. That was one I mentioned briefly. Do you understand how to get the difference quotient? Yeah. Okay. So did anyone want me to do the difference quotient for this one? Was the one? This is 1.10 number 2. So that's where you go. What's this? S of, yeah, don't worry about the interval, but don't worry about this thing. But it's S of 7 minus S of 3 all over 7 minus 3. Okay. And then your average velocity is in meters per second. Okay, that's how you work. That's how you would work out 1.10 number 2. Okay.
What is that formula though?
This?
Like, where do you get that formula? Like, where does that come from?
That's average rate of change.
Okay.
It's average rate of change, yeah. So maybe, do I have the notes up here?
It's
Yeah,
just the same as the slope formula, right?
yeah.
Yeah, that's I got it.
Yeah, but it's good to show it. I have it typed, so it's 110. Right. So it's the slope of the secant line. It's that in terms of f. For the s function, this is the more specific form for the average velocity. Because remember, average velocity is the rate of change of position with respect to time. So the the dependent function is specifically a position function, S. Okay, but it's the same idea as before. Yeah. Okay, meters per second. 161E. Linear combination. Okay, so the rule just goes so h of x equals, so this is from E, right? H of x equals 2 times the square root of x plus 3 times the quantity, the square root of x minus 4. And you can simplify that. But it's basically 2 times f of x plus 3 times g of x. The domain, well, the only restriction is that x has to be non-negative. So the domain for both should be this. Yeah. Oh, yeah. Okay. So yeah, the non-negative reals is the domain. And then when you simplify this, 2 root x plus 3 root x is 5 root x minus the 12. Right. 5 root x minus 12. That makes sense. Here's a setup. All right. Okay. At the end, 133, we didn't have symmetry about the h-axis. Okay, the domain was not symmetric about 0.
Yeah, well, h equals the square.
Right. Okay, I think I hit the chat questions. Any more questions? Yeah, go ahead.
I have a question on 1.7, 1C, and 1D. How do you prove that those are neither?
All right. State whether even, odd, or neither. Okay, now here's the thing. On number 1, you technically don't have to prove it, but I'll put it this way. On 1C, you see why it's neither, right? Because it's a polynomial in descending powers, and you have a mix and even and odd exponents on x, right? So do you see the shortcut that this is neither?
Yeah, but I'm just confused because for D, aren't all the exponents odd, but it still says it's neither?
No, because 2 is 2x to the 0. Remember?
Oh.
Yeah. Be careful. All even I'm sorry. All constant functions are even. All constant functions are even. But yeah, that was the trap. You're right that if we just had these first 3 terms, the function would be odd, but the plus 2 is a killer. It moves you away from the origin. See, the graph of y equals these guys, that goes to the origin. When you put in a plus 2, you're moving that guy away from the origin. So this guy kills it.
Okay.
Right. So something like 2 represents an even function and not an odd function. The 0 function is the only constant function that is both even and odd. Which is why you can do plus 0. That's a wild card. In terms of a proof, I wouldn't have people prove the neither case, but technically you could take 2 opposing values for x and show that the function values are neither equal nor opposite. I did a counterexample like that in the notes, but I wouldn't expect students to be able to necessarily do that. Although, it's a nice exercise. Technically, you would prove a neither case by counterexample.
I'm sorry. I know it's really late, but I really just don't understand piecewise functions. So like on that question 2b on for 1.5, I just don't understand because how is -2 the answer? Because -2 is not bigger than -1. It's less.
Okay. So we're asking you to evaluate g of -1. -1 is an x value, right? And we're asking which subdomain does it belong to? -1 satisfies this compound inequality. Okay. Because -1 is not less than itself. Okay. -1 has nothing to do with this. X equals -1 is only contained within the second subdomain, the middle one.
Oh, okay. So it's not about the answer. It's not about the answer when you substitute. It's about what the x is when you substitute.
So the subdomains involve the inputs, the x coordinate.
Okay.
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 And then when you plug into the appropriate rule, in this case 3x plus 1, you're getting the function value or the y coordinate. So in this case here, this means that the point -1, -2 lies on the graph. And I think I think I have it on here somewhere. Okay, where I graphed it. This is
Professor, did you go over 1.61e?
yeah, okay. Wait, what was that again?
1.61e, the linear combination. I looked at the notes and like tried to figure out how to do it, and I like was just genuinely confused on where to start.
H of x equals 2f of x plus 3g of x. All right. So h of x equals 2 times root x plus 3 times this quantity. That's what I have written here. And then you would distribute the 3 and simplify. Basically, the rule for h of x is given by a linear combination of the corresponding rules for f and g. H of x equals 2 times f of x plus 3 times g of x. Here's f of x. And here's g of x.
Okay, that makes sense. I thought it was... Okay, that's easy.
All right. It's 9:59. I got a little bit of a second wind. I was getting a little sleepy at some points, but I'm trying to pick up again. Any questions? Any questions?
I'm good, Professor. Have a good rest of your night.
All right, take care. Have a good weekend. Yes. All right, any other questions?
Okay, this is my last question. For 1.9, number 4, why is it yes?
1.9 number 4. All right. Right, because if a function is increasing, okay, now if it's a function, it passes the VLT. If it's increasing, it also has to pass the HLT. That's the key thing. Because the one-to-one property, the key thing there is that the graph not only passes the VLT, it also passes the HLT, the horizontal line test.
Okay, got it. Thank you.
All right, because the graph's always going up, up, up. You're not allowed to go flat. An increasing function is not allowed to go flat. All right. 125D. Okay, 125D. Find the x and y intercepts of the graph. All right, the y-intercept is the easier because you plug in x equals 0. Y-intercept, plug in x equals 0, and you get -1, right? F of 0 is -1. It's -4 over 4, okay? So the y-intercept is at 0, -1. That's the easier one. The x-intercepts are harder. Okay, that's when you set this guy equal to 0 over here. All right, so when does a fraction equal 0? A fraction equals 0 when the top equals 0 and the bottom is not 0. Okay, certainly with a nice rational expression like that. All right. So we need 5x squared plus 19x minus 4 equals 0. And x cannot be -4. All right. You could use a quadratic formula, but I think old school factoring works here. Let me try to remember. I think old school factoring works. Oh, no, it doesn't. It doesn't. Wait, is that? No, maybe it does. I think it does, actually. 5x. Yeah, it does. 5x and x. 4, 1. It's a positive 20x and -1x. Yeah, this works. This works. All right. So the now the corresponding zeros would then be 1/5 and -4. But wait a minute, -4, that's illegal. So I got to kill this guy. 1/5 is the only value for x that makes this equal to 0. X equals -4 makes this undefined. So the x-intercept is at 1/5, 0. Right. Okay, 132A. How do we prove that GFT is odd? All right. So basically, to prove even or odd, you want to analyze, in this case, G of what? The opposite of T, right? So G of opposite T is the opposite of T all to the 5th plus the opposite of T all to the 3rd plus the opposite of T. All right. This turns out to be opposite of T to the 5th minus T cubed minus T, which is the opposite of the given rule. It's the opposite of G of T. For all T values in the reals. So when you replace t with its opposite, you get the opposite. Domain is all real. So the domain this time is symmetric about 0. It's not the same problem as that falling coin problem. The domain is symmetric about 0. Okay, so when in doubt, to prove even odd, replace the argument with its opposite and make sure the domain is symmetric about 0. If the domain is R is symmetric about 0. All right. Anything else? Anything else? Okay, any questions? Any questions? Okay, any questions? Oh, okay. I have a, what do we have here? 1.25C again. Is this one too? Well, I went over 5D. 5C. Yeah, I don't even know if we did 5C on Tuesday, but yeah, I can go over that. Let me get a fresh. Yeah, here we go. Okay. Now again, the y-intercept is fairly straightforward. You set x equal to 0. We basically evaluate f of 0, and we get what? The square root of 9 is 3. Therefore, 0, 3 is the y-intercept, right? Okay, so that's not so bad. The x-intercept, or intercepts, if any, that's harder. That's when you set y or f of x equal to 0. And you're solving an equation. You're actually solving an equation. That tends to be harder. Okay, so we have 0 equals the square root of da-da-da. Although the nice thing here, though, is that we can make the following observation. When is the square root of blah equal to 0? That happens if and only if blah, the radicand, equals 0. So that basically means we can square both sides. We can analyze the radicand. So 0. So this happens if and only if 0 equals the radicand. 9 minus 3x minus 4x squared. All right. Now, you could work with it directly, but I think it'll be nicer if we add 4x squared, because I like positive leading coefficients. Add 4x squared to both sides. Add 3x to both sides. Subtract 9 from both sides. Okay, and this is a more popular form. Unfortunately, this thing does not factor old school. If you don't believe me, check out the discriminant. It's not a nice perfect square. Is it 130? Is this the one that's 137? That sounds familiar. So, or 153. It's 153. Discriminant's 153. All right. So use the quadratic formula. We got to use our old friend, the quadratic formula. All right. A is 4, B is 3, C is -9. All right. X equals opposite of B plus or minus square root of B squared minus 4AC all over 2A. So we have the opposite of 3, or -3, plus or minus the square root of, I just worked this out. This was 153. It was 153. That was a discriminant. All over 2A. Which is 8 down there. Now here's the tricky part. Root 153 can be simplified. And I have a hint here. Divisibility by 9. If you look at 153, the digits 1 plus 5 plus 3, if you add up the digits, it's a multiple of 9. That means this is divisible by 9, actually. It's 9 times 17, I think. Yeah, it's 9 times 17. So it's not super obvious, but 153... 153 is 9 times 17. All right. So we have here -3 plus or minus. The 3 pops, sorry, okay. So root 153 equals root 9 times 17. Root 9 is 3. And then you have root 17. All over 8. And technically we're dealing with x-intercept, so it's these two numbers, comma, 0, technically speaking. Oops. Yeah. So -3 plus or minus 3 root 17 over 8, comma, 0. Right. Uh, 121. Okay, now first this is 125C, right? All right. 1121. Oh, right. Many students have asked me about this. The basic idea is that if A is in the domain of a function, right? For a given input in the domain, how many outputs can you have? You can only have one output, which means that if f of A is A squared, and if f of A is 6A minus 9, these better be equal to each other, right? If you have equal inputs, they must yield equal outputs. Otherwise, you don't have a function. So I worked this out with a student before. You said A squared equals to 6A minus 9. Isolate 0 on one side. That's a PST. Factors like that, A is 3. So part of it was the algebra, but more than anything else, it was the understanding of how a function works. If you input a function from the domain, you get exactly one output in the range. These expressions must be equal to one another. Oh yes, it wasn't meant to be mechanically hard, but I can understand students wondering, well, what do I do, right? I mean, I see these easy expressions, but what do I do? The answer is to set them equal. Just because it looks easy doesn't mean it is. It's the last problem. It's often the hardest. Right. Okay. Any more questions? I'm willing to go to 10:30, but I can understand if you're tired. There are a couple of moments when I was starting to fall asleep too. I had to get some chocolate. All right. Any questions? Or if you want me to wait 5 minutes. All right. All right. Any questions, or if you want me to wait a few minutes, gather your thoughts. You can gather your thoughts. All right. Thank you. Yes, and have a good weekend.